Let's see how you're doing on these. If you're not done, that's okay. Let's see how you've done and what you got done so far. For this first one here, it's a rather long problem again. I'm going to show you how I cheat on them a little bit. Rather than rewriting the problem at every step, I rewrite the problem once. And I realize this is a little bit easier with me having the computer screen because the erase is clean and your paper may not. But I go through and I just erase and replace what I'm doing instead of having to rewrite the whole problem at every step. So looking at this to begin with, where am I going to start? Okay. So I have my first set of parentheses here going left to right. That's the first one I run into. And now inside there, I keep going with order of operations. So what's inside there that has to happen first? Okay, the first set of parentheses again. So we're inside that purple box for now. In there, are there any other enclosing symbols? No. Exponents? Yes, there are. 4 squared is 16. So erase the 4 squared and put in a 16. Any other exponents? No. So I go down multiplication and division. Yes, so 32 divided by 16 is 2. So again, I erase it and replace it with a 2. Now I've reduced that parentheses to a single number. I don't need the parentheses anymore. Do I have to do anything when I take the parentheses out here? I have to put in the multiplication, yes. There was no symbol here in front of the parentheses, between the 3 and the parentheses, so I do have to put in multiplication. Now I can move to this next set of parentheses. I'm still working inside the parentheses that have the green box there, but I'm still applying my order of operations. There's another enclosing symbol, so I move over to this set of parentheses. All that there is to do in there, of course, is 5 minus 3, which is 2. Now that parentheses is reduced to a single number, so I can get rid of them. Do I have to put anything in when I remove those? Perfect. There's already an operation on both sides of that parentheses, so I don't need to add any operations in there. So now I'm still inside that parentheses that's the green box. Any other enclosing symbols? No. Any exponents? No. Multiplication, division? Yes, there's a few of them. So we're going to go left to right. We first have 3 times 2, which is 6. Next we have 3 times 4, which is 12. So that's all of our multiplication and division. So next it is addition and subtraction. So again, we're moving left to right. 7 minus 6 is 1. 1 plus 2 is 3. 3 plus 7 is 10. And 10 minus 12 is negative 2. Bless you. So now we've reduced what's inside that parentheses to a single number, but I'm not going to remove the parentheses. I'm going to change the meaning of the parentheses, but they're still going to have to be there. Because that's a negative 2, I'm going to leave the parentheses around it so I know that that's a negative 2 and not subtracting 2. So that parenthesis stays there, but it's no longer an enclosing symbol. It's just isolating the negative 2. Oh, should be 13, thank you. So now that parentheses is not telling us to do anything. So we can ignore that. Any other enclosing symbols? No. Any other exponents? No. Multiplication and division. Well, there's a couple of them. We do have the 2 times negative 2, which is negative 4. And again, I'm going to put it in parentheses so I know that it's a negative 4, not subtracting 4. What's next? 2 times 7, which is 14. and no more multiplication or division. So we are on to addition and subtraction. We have 13 plus a negative 4 is 9. 9 plus 14, 20. How many of you got 23? Okay. Anybody have any questions? Want to go back over one of the steps or how we got to it? Okay. There's just a lot of little steps to mess up there. Like I said, the biggest mistake most people make is they want to add that 13 and 2 right away. That's one of the last steps that we can do. Down here, that fraction bar, if you recall, is an enclosing symbol. So that means we can't do anything with it. We have to do everything on top first, everything on bottom next, and then we can do the division. So let's do the top. What do we do first there? 5 times 7 is 35. And then 7 divided by 9 is 3. And 35 minus 3 is 32. So our top is the 32. On bottom, what do we have to do first? Exponent. 3 squared is 9. And then 54 divided by 9 is 6. 5 plus 6, 11. So we've got 32 over 11, which is 2 with a remainder of 10, or 2 and 10 11ths, however you did it out. Didn't come out so well, did it? Okay, and as we move into our next units, of course, we'll figure out how to turn that into a fraction or a decimal or whatever form we want it into. Okay, so that kind of ends our exploration of whole numbers and integers. We talked about negatives, just a little bit to recall. Think if I have negative 37 minus 42. We change that. We're going to change that to a negative 37 plus what? Negative 42. It's negative 37, negative 42. We know they're both in the negative direction, so they're negative, and that go through the same direction, so we add their values, add the absolute values. So that's a negative 79. So we also worked with those integers, those negative values. And as we get into decimals and fractions in future units, we'll keep coming back to those negatives and how we work with them. Today we want to start talking about variables and what can we do with variables. Algebraic numbers. A variable has several different meanings it can take on, 7 different purposes. It can be a placeholder. In other words, it's sitting there waiting for a value to be assigned to it. We use this in formulas all the time. In the trade and technical areas, it's probably the biggest use of a variable. You have formulas in machining for cutting speed, time to cut, calculating RPMs, stuff like that. In business, you have formulas for interest, annuities, markups, markdowns, and all those sorts of things. So one of the biggest applications is that formulas. It can also just be for writing a generic expression. And we'll look at some of those in a little bit. The second thing it can do is it can serve as a calculatable value. I'll put it as a value to calculate. Where it has a specific value, we just have to find it. And we'll actually look at that a little bit in our next class. And then the third and final way is just simply to represent an unknown. Or a general value. In other words, we can use it to define a rule that applies to all numbers, no matter what they are. Show you a couple of examples of this quick. We talked a little bit about commutative when we talked about negatives. There are properties of numbers, rules for working with numbers that apply to any number in the correct situation. For example, for addition, there's a commutative property for addition that states A plus B is always equal to B plus A. So here, A and B don't represent any particular value. They represent any possible value. I can pick any number for A, and I can pick any other number for B, positive or negative. And when I add them together, it doesn't matter which one I start with. They're going to end up being the same. Let's say A is 5 and B is a negative 12. Doesn't matter which one I put first. It's going to come up to be the same value. I can start at 0 and I can go up to 5 and then back negative 12 to get negative 7. Or I can start at 0, go to negative 12, and come back up 5 to get to negative 7. Either way, I end up at negative 7. That property also applies, by the way, for multiplication. A times B equals B times A. We looked at that a little bit last week when we looked at 5 times a negative 3. Definition of multiplication doesn't allow us to take 5 and add it to itself negative 3 times. So we had to switch that around and say, okay, that's negative 3 times 5. We're taking negative 3 and adding it to itself 5 times. That makes more sense. There's associative rules. This deals, again, only with addition and multiplication. I should put multiplication down here. So in our associative rules, we're dealing with adding or multiplying 3 numbers. If I have A plus B plus C, our order of operations say that if it's written like that, we should add the first 2 together first, right? We should do A plus B and then add the C. Now, I don't really need the parentheses because order of operations says you're going to go left to right. But the associative rule says if it's all addition, I can add the last 2 first if I want to, and it doesn't change anything. And again, the A, B, C, all that's saying is I can put any numbers I want to. I can randomly pick numbers. I could do A is 5, B is 27, and C is negative 3. Well, 5 plus 27 is 32, plus a negative 3 is 29. Well, if I have 5 plus, and then I do the 27 plus negative 3 first, 27 plus negative 3 is 24. 5 plus 24 is still 29. I do get the same result. And the same is true. You okay? Same is true for multiplication. If I'm multiplying 3 numbers, A times B times C. Order of operations says I would naturally multiply the first 2 and then take that result times the third one. But again, since it's all multiplication, I can cheat the order of operations a little bit and multiply the second 2 first. Notice these properties do not apply to subtraction and division, only addition and multiplication. And there are identity rules out there. For example, if I take a number and I add 0 to it, what do I get? Same number, yeah. So again, all that's saying is any number, if I add 0 to it, I'm going to be left with the same number. Or if I take a number and I multiply it by 1, I'm going to get the same number. So that's one of their applications of a variable, is just to fit a generalized number. It can be any number. We're defining a rule. What's that equal? That's a divided by 0. Well, let's pick a number and try it. Let's try 7 divided by 0. Careful. A lot of people want to say that. Punch it in your calculator, though, what does it come up? Your calculator is going to say error. You can't do it. Dividing by 0 does not work out. Remember when we talked about our negatives? Division, 7 divided by 0, is asking what number times 0 equals 7. Well, if I multiply by 0, what do I get? 0. There's absolutely nothing that I can put in here that I can multiply by 0 and get 7. It doesn't work. Therefore, we cannot divide by 0. Dividing by 0 is a very bad thing. It'll give you an error in your computer or in your calculator. If you had a computer program running that required you to divide by 0, it would shut down the program and give you an error. There's actually a very famous example of this from the late 1980s. When they first started doing satellite navigation in the Navy, the large ships, they had a program that all they would do is punch in the coordinates that they wanted to go to, and it would actually access the satellite, get their current coordinates, and then calculate the most efficient path to get to where they needed to go. And they've been using it for over 1.5 years without any issues. And it just so happened on that coordinate, they were in a coordinate where when they subtracted their coordinates in the formula, it gave them a 0, and they divided by 0, locked up the battleship's computer. They had to completely shut down the whole system and reboot. It took about 12 hours to shut down one of those systems and reboot it. So you had a $1 billion ship sitting in the water dead for 12 hours because somebody tried to divide by 0. So, I mean, obviously most of the examples in your life won't be quite that extreme. Once we talk about solving equations later in the week, remind me, and I will go back and I will show you an example of dividing by 0 where really weird things happen. Okay, so that's one of our applications of a variable, is to define rules. The next application we want to look at is just, it's a general expressions where it has a value, we just haven't assigned that value yet. For example, we might say a number increased by 6. So we can represent this missing number with any letter or symbol we want to. We can call it A, B, C, X, Y, N. Sometimes we use Greek letters, alpha, beta, pi, theta. We're going to typically use X or N. In my math lab, when it asks you to define this, be really careful, because what it'll do is after the blank where you're supposed to put your answer, it'll say use M or whatever for the unknown for the number. So whatever letter it tells you to use, you have to use, or my math lab is going to mark it wrong. So here if it says use M for the unknown number, it's M is my unknown number. What does increased by 6 mean? Add 6, plus 6. So it's M plus 6. Now there are a lot of other phrases out there that would indicate M plus 6. We might have 6 more than a number. You might have a number plus 6. Anybody think of any others? The sum of a number and 6. 6 added to a number. 6 more than a number. There's all sorts, I got more of that already there. There's all sorts of them out there that can indicate n plus 6 or m plus 6 or whatever variable you want to use. Now this one here, this is a wording that tends to confuse people. This does not say 5 is less than a number. It says 5 less than a number. To get 5 less than a number, what do we have to do? We have to subtract 5 from something. So I'm going to let my number equal x for now. So x minus 5. If this said 5 is less than a number, what that would be asking for is this. 5 is less than x, like that. Very seldom will you get asked to translate something like that, though. Usually we're looking for an expression like this. So other expressions that would translate into x minus 5. Well, number reduced by 5. Any others? Number minus 5. Anybody think of any others? Difference of a number and 5. Now, one thing I want to point out here, all of these mean x minus 5. All of these meant m or x or whatever plus 6. Would it have mattered if I put 6 plus m here? It's the same thing, yes, because addition is commutative. We can change the order. Down here, would it have mattered if I put 5 minus x? Yes, that is different. I cannot do that. So you have to be very careful. A lot of people, that's why I did this wording like this at first. 5 less than a number, because a lot of people want to put the 5 first because it comes first. But 5 less than means the 5 is being subtracted from something. How about this one? A number repeated 3 times. What's that going to be? 3 times x, or it could be just 3x. We don't have to put the times in there, right? And again, it could be any variable. You could use n, p, whatever you wanted to do for the missing number. Again, be careful in MyMathLab, so make sure you see what it tells you to use. Other expressions that mean 3x or 3 times x. Three multiplied by number, or a number multiplied by 3. Remember, when we're multiplying, if I did x times 3, does it mean the same thing? Yes, it does. For multiplication, that's okay. We can switch the order. Any others you can think of? 3 multiplied by a number, or a number multiplied by 3? Three times the number. Similar to the difference of, or the product of, or the sum of, we have the product of a number and 3. So either product of a number and 3 or product of 3 and a number. Let's look at the last one. A number split 8 ways. What's that going to be? X divided by 8, or x over 8. Remember, fractions are equivalent to division. Other expressions that mean x divided by 8 or x over 8. Perfect. Quotient is a result of a division problem. The quotient of a number and 8. Any others? I'll state the obvious one. A number divided by 8. A number over 8. 8 going into a number. There are several of them, again, that could mean a number divided by 8 or x divided by 8. Well, those aren't so bad because they're simple single operations. Where it gets to be more complex is when we add in multiple operations like this. 8 more than 5 times a number. What's that going to look like? Let's take it each. Go ahead. 8 plus 5x works. There's another way it could have been written as well. 8 more than means 8 plus or 8 added to something. Could have been written as 5x plus 8. Both of those would be correct answers for this. So in your notes, as I write these next ones out, try to find a formula for it. Five times the number increased by 8. Eight more than the product of 5 and a number. Five times the sum of a number and 8. I'll give you a minute to think about each of those and get an answer written down. Let's see what you have done so far. 5 times the number increased by 8. Well, 5 times the number is just 5x increased by 8 plus 8. So exactly the same as what we had up here. 8 more than something means adding 8 to something. 8 more than the product of 5 and a number, 5x. So once again, 5x plus 8. 5 times the sum of a number and 8. Yeah. Yes. Notice here, this is 5 times a number, the product of 5 and a number. In all those previous examples, 5 is multiplying the number. Here, however, it says 5 times the sum. The sum is the result of an addition problem, which means we must find the sum first. So it's 5 times some addition problem. The sum of a number and 8 is x plus 8. So there's just a very slight difference in the wording makes a big difference in what it looks like. Any questions so far? Okay. Okay, so next we're going to start doing some calculations with these. So the last application of our variable we're going to deal with is in a formula where we have to replace the value. So the final application we'll work with in the next classes where it has a value, we just have to determine what it is by solving the equation. For today, the last application we're going to look at is in a formula. Let's say we have something simple like that. 5c minus 2a for c equals 7 and a equals 4. The command we'd most likely be given would be evaluate. So evaluate means to give a value to. We have this algebraic number here, this algebraic expression it's called. And we want to evaluate that expression. We want to give that expression value for c equals 7 and a equals 4. So all that means is we are replacing the letters in that formula with those values. So instead of 5c, which of course means 5 times c, this becomes 5 times c equals 7. So 5 times 7. Minus, instead of 2a, which means 2 times a, it's 2 times 4. And now it's simply an order of operations problem. No enclosing symbols, no exponents. So we're going to go left to right. 5 times 7 is 35. 2 times 4 is 8. So 35 minus 8 is 27. So for c equals 7 and a equals 4, 5c minus 2a evaluates to 27. We can have a little bit more complicated formulas. So we may have 6b squared minus d times, and in parentheses 15m minus 2d plus 3. And we're going to evaluate that for b equals 5, d equals 3, and m equals 4. Bless you. So, as I rewrite this becomes 6 times 5 squared, replace b with 5, minus d is going to become 3, times, in the parentheses, 15m becomes 15 times 4, minus d squared is going to become 3 squared, and then plus 3. So now we're back to an order of operations problem like we did last time. What has to happen first here? 3 squared. In the parentheses, we got to do the exponent first. 3 squared is 9. Now we're still in the parentheses. What has to happen next? 15 times 4, which is 60. And then 60 minus 9 is 51. And finally, plus 3. Yeah. 51 plus 3 is 54. So now my parentheses is reduced to a single number. I can get rid of them. And I do have to remember to put in multiplication. What's next? 5 squared, which is 25. And now, all I have left is multiplication and then subtraction. So I'm going to multiply first, left to right. 6 times 25, 150. 3 times 54, 162. And we subtract to get negative 12. Any questions? So in your notes, I want you to try to evaluate six c plus 2m squared over 4p plus, or 3p plus 4d. Evaluate that for c equals 8, m equals 3, p equals 2, and d equals 3. So I'll give you a minute to do that in your notes. Let's see how you're doing so far. So this is going to become 6c. It'll become 6 times 8 plus 2m squared is going to be 2 times 3 squared over 3p is going to be 3 times 2 plus 4d is going to be 4 times 3. So now we have to do the top first. What's the first thing that needs to be done up there? The exponent. 3 squared is 9. And then multiplication. So 6 times 8, 48. And 2 times 9, 18. So 48 plus 18 is 66. So the top of this is 66. On bottom, 3 times 2 is 6, plus 4 times 3 is 12. So 6 plus 12 is 18. That divides out to be 3 with a remainder of 12, right? For now, we're 3 2/3 if you divided it out, 3.666. Any questions so far? Now our next step then, before we get too far into these, is we can add a symbol. Rather than just having that expression that we're going to put values into, the expression might mean something. One of the more famous ones is degrees Celsius to degrees Fahrenheit. So we might have Celsius equals Fahrenheit minus 32 times 5 divided by 9. So for this one, let's do, got to come up with a good number here that's going to work well. Let's evaluate this for f equals 50. So we put 50 in for f. What do we have to do first here? We have to do everything on top, and on top we do have the parentheses first. So 50 minus 32, 18. Now I'm going to skip a step and I'm going to take the parentheses out as well because I've reduced what's in that parentheses to a single number. 5 times 18 then is 90. So this is 90 over 9, which divides out to be 10. So what this is saying is C equals 10. So the Celsius temperature equals 10. At some point, we're going to go the other direction where you might be given a formula like this and be told if the Celsius temperature is 20, what was the Fahrenheit temperature? And that's something we'll look at in the next couple of classes, Wednesday and Thursday. We'll look at, okay, we put the 20 in for C, and then we have to figure out what F is, working backwards. For now, we're going to give you a separate formula. The Fahrenheit temperature is equal to 9 times the Celsius temperature divided by 5 plus 32. So if the weatherman says it's going to be 20 degrees Celsius out there today, is it going to be a warm day, a cold day, or somewhere in between? Well, we put in the 20 for C, so it's 9 times 20 divided by 5, then plus 32. What do we have to do first? 9 times 20, which is 180. What's next? Divide by 5. 180 divided by 5 is 36. 36 plus 32, 68. So that'd be a 68 degree Fahrenheit day. For me, that's about perfect. Maybe a little chilly for some. But. Any questions? So if P equals let's do 3D minus 1 over 13 plus 5D plus 3 over 16. Find P. So in your notes, find P for me. So this is basically two problems combined into one. We have to do this first piece here first. And of course, we have to do what's on top of the fraction bar first. So on top of that, what do we have to do first? Multiplication. 3 times 9 is 27, minus 1 is 26. So we have 26 divided by 13 is 2. Now we move on to the next fraction bar. Again, we have to do what's on top first. 5 times 9, 45 plus 3, 48. Good. 48 divided by 16, 3. Now, for some reason, a lot of people usually forget this part. We have to do the 2 plus 3 is 5. Any questions? Okay, it is time for a break, so let's go ahead and take a break. We'll come back at 9:30 and start lecturing again.